Hey everybody, thanks for coming back. So, who's been at an Acronis event before? Anybody been at an Acronis event before? We have an evening event. We're very, very proud to host it. And something that's very close to our heart in Acronis is women in tech. And we're very proud to present this tonight, which is five very, very well-known females presenting on their industry and their knowledge about their industry. And it's something that, as I said, very close to the Acronis heart. We've got Susie Wolf, who's an ex-Formula One driver. She's now running, she's the team principal at Rocket Venturi. We've got Claire Williams. We've got some of the Williams team here as well today. Claire Williams is the deputy team principal at Rocket Williams Racing. We've got Cheryl Robinson, who's the founder of Ready to Roar, and she's also a contributor to Forbes. And Asil Al-Hamad, who's an entrepreneur and also a representative of women in motorsport in Saudi Arabia. Jamie Chadwick is the development driver for Williams. So five very, very intriguing ladies to come and see tonight. And we're hosting that event out by the pool at 7 o'clock. So this event will finish about 5:30. And about 7 o'clock, we will be out in the pool where we'll have some food and drinks and and listen to some dialogue between the five ladies here. I'd like to introduce Mauro Pezze. Mauro is from the Schaffhausen Institute of Technology. We have a great relationship with the Schaffhausen Institute, and Acronis is leveraging the skills that exist in the Schaffhausen Institute of Technology, and Mauro is going to tell us a little bit about that. Thank you, Mauro.
Hi, thank you. Thank you, everybody. I think my job today is, or my task today is to switch context. You know, you got these very nice presentations this morning with ideas and products, so basically solutions and products, which is what you expect from a company. Now I'm coming from a university, so I move from ideas and products to problems and new ideas. So we move from the concrete to the abstract. We move from the today for tomorrow. And I'd like to give you a couple of information about the institute, SIT, Schaffhausen Institute of Technology. It's going to be known in 5 years as the most important center worldwide, but we started this year, so it's going to be difficult to actually be so known at the very beginning. It's a new institution. It's a brand new institution, which is actually coming from the idea of pairing innovation products with research and future. It's coming from the idea of putting together a completely new center for academia and research, which is based on three legs, which is actually academia, education, which is innovation, research, which is technology transfer, technology center. And the completely new idea of this institution is focus. We are not a general university with the Faculty of Law, the Faculty of Medicine. No, we are a school of digital technology. The idea of this school is really to think about digital technology from the A to Z. Is to go from informatics, cybersecurity, AI, software engineering, robotics, to what we need to build the new generation computers, which is quantum technology and advanced material, and how we actually can impact on the society. And this is actually the winning part. The other thing is, I don't have faculties, I don't have departments, I have ideas, I have groups. The idea is to have a completely interdisciplinary institution without borders, without breaking points. And we are located in Switzerland, in Schaffhausen, of course. We are located in Schaffhausen, and being 3 months old only, we do have a joint master program with Carnegie Mellon University in US. We do have a joint master program with National University of Singapore. We are discussing a new joint program with Cambridge, and we will have our new program in Schaffhausen next year. So that's actually a very fast-growing idea. Now, let me move from the institution to the problems, okay? And I promised you, no solution, just problems. The problem is runtime failures. Okay, and unavoidable. Okay, I think we know that. We saw this morning how we can prevent, protect, make it secure, reduce. We cannot avoid them. No matter how good you are, failures will be always there. We have a very nice study that says, look, there is no way to get rid of failures, and they are expensive. Again, I don't have to tell you this audience, but they have a couple of numbers, which I just read because I'm not in the industry, but I got these huge numbers here, like $2.5 billion for total cost of lifetime application per year. You get like 1 million per hour. I mean, this is a number that scares me. And that actually inspired our solution, which is basically our idea, thinking about a new solution, which we call self-healing. I say cloud system. Can be self-healing system. So I just moved to self-healing cloud system because that's what we experimented with, and I don't want to claim that we do more than that. What it means basically is assuming we cannot avoid the runtime failures, and I can give you a lecture about that. What we can do is we can prevent, tolerate, and remove failures. So the idea is not to actually make sure, and not to get rid of what we know and have already, but go ahead and say, okay, even if we do our best, we will fail, and we want to actually prevent it. By what? Well, 4 legs of our research, which is predicting failures, locating bugs, working around failures, and fixing bugs. And I will go through these 4 steps very quickly, okay? But before that, I want to make sure that we understand that we do something which is really new. Because, you work, many of you are technical people, and, be working with OpenStack, with Kubernetes, again, cloud solutions. Here's a full list of products that allow you to monitor, to recover hardware system and POD problems. What do we need then? Well, big performance inferences, if you adopt them flat completely, you get crazy without performance problems. And there is no knowledge. These tools are completely unaware of the applications. They are a basic. This is what we build up top of. It's not what we have right now. Okay, so basically what we do is we move from the current limitations, what we have, what we actually feel we want actually to avoid, to the new features. I call this this research star, okay, it's not a product, it's the name that I've been using in my career to indicate my lab, and this star lab is now Schaffhausen. It used to be Lugano, it used to be Milan. It's actually my history, and I carry on my students and my group in this way. But then basically let's call it star, and we want to have limited performance interference. We want to really get rid of performance interference. We want to actually know about the application and have a holistic view, and this is what we want to do. So what have we do? Basically, this is the idea. This is the bad part of the story. At some point in the lab for your system, you have a fault. The fault is activated. What does it mean? It changes the state. You get to what we call an error state, and you stay in an error state, and then you fail. And what we want to do is we want to actually predict the failure before the failure occurs. Once you inject, you have time to predict it. Oh, you want to actually to localize the fault. Why the hell? Once you know that it's going to fail, why we need to localize it? Well, one of our early partners had 2 million nodes in their network. And they say, if you say it's going to be failing, it's not good enough. I want to know where. Okay, and then we want also to heal, which means basically get rid of the failure and go to normal state. And that's what we are trying to we aim to do, and we do in many cases. Now, let me show you how we do that. We have our nice system. Of course, we have sensors, actuators. We have monitoring. I mentioned something about monitoring, but very, very little. We have 3 steps: prediction, localization, and healing. And now, I can stay here for the whole day, telling you all of the results we have, but I actually give us a very, very big overview of what the technologies, the idea that we use, and then I'll be around for the whole day if you want to know more. Basically, monitoring. Monitoring is easy. Okay, this is actually a typical cloud stack. Now, if in general, what you do is you already existing monitoring. So we use, for example, Linux server monitoring, OpenStack monitoring, Clearwater monitoring. Now, it's not really important what we use. What is really important is that systems already have a lot of capabilities of collecting metrics. And so that's why it's low impact. We don't need anything more than this, basically. Now, the other thing we want to do is we want to go ahead, and this is the most interesting part, which is predicting failures. Okay, now I have 1.0, you get 2.0, 3.0, because we started a long time ago and we get success and failures. I think now we get success and success. So let's say, but I give you to the failures because I give you why we actually went to the next step, which is basically, first part is data analytics and machine learning. We started 7 years ago about that, and we actually did the following. We actually have detect anomalies. Okay, you want to know now my fault is silently corrupting my state, but there is some anomalous behavior. And then we want to actually classify anomalies so that we can say, this is reasonable, well, this is not. Okay, and what we use basically data analytics. Data analytics is a great technique to actually get information about what we call monovariate anomalies, which means one single metric, one single key performance indicator. You get this is out of range. Okay, what does it mean? Maybe it's a peak of traffic. Maybe there is Acronis coming to Abu Dhabi and you have more people using the same devices accessing, and that's an anomaly. That's very likely a good anomaly, you know. But then you want to actually pair it with machine learning, and we experiment many things with deep autoencoder, which is, for the people who know it's obvious what it is. For the people who do not know, it's basically one of the many machine learning approaches. What you do basically is you actually try to classify, and that's a classification. You want to distinguish between spurious and failure-prone anomalies, or failure-prone KPIs. And so you have single KPIs who are anomalous, and they say, look, which one are bad and which one are good? Now, the red one are the, well, depending what you be, my point is the good ones because they're the failure one. The one that I want to actually identify. For you are the bad ones, what you want to avoid, you know. But you know, I want to identify those ones and not the blue ones, which are the good ones for you and the bad ones for me, because they don't care. Actually, they are the false alarms. And this little line says how good we are in identifying them. Now, if you look at that, you know, it's I think it's actually 98.99% of success rate, which is fairly high, actually, I would say. And now, once you know that, we have very precise prediction. We also get fault localization. Oh, but we need extensive training with fault injected in the system. And when we told this to our first industrial partner, large telecommunication company, that says, no way, actually inject failures for weeks in our system to get your model running. So we moved on to failure predictor number 2, which is machine learning only, because it's actually data analytics, the one that actually breaks our things. And then what is data analytics? Basically, we actually get to the same part, and what we do is we use one class support vector machines. Again, the one of you who are in the business know what I mean. The one who are not, it's yet another nice machine learning technique that you can use to actually analyze big mass of data to get some information about them. And we can actually get good failure alerts, but no failure localization and no failure prediction. So basically the idea is we know what the system fails, but we miss the second part, which is, we don't know where, and we don't know what. And so, precise failure prediction, no more localization, but without, no seeded faults. We can train the system. We still need weeks for training. Actually, right now we have the new experiments running with weeks to get data. And again, great for some companies. We have been successfully talking to banks, for example, where the system is very stable, is very static. When we went to people using a dynamic technology, disaster. You know, because, you know, how the hell can you actually train for 2 weeks if your system changes every 5 minutes? Okay, and so we went to the next one, and the last one for prediction, which is 3.0, which is basically, we moved on. This is a great idea. You know, I got a PhD student who has a PhD in physics, in theoretical physics. What the hell you do in theoretical physics as a computer scientist? She came up to me telling me about magnetic properties of the materials, and she tells me, look, you know, the magnetic property of the material is actually driven by the spin, the alignment of the spin of the particles. What has to do with us? Well, we look at a specific property, magnetism. In the case of physics, we look at failures in our case. That's a specific property we care about. And we look at particles, spins. We look at particles, anomalous KPIs. And we get up with an energy-based model using deep learning. So what we do is basically we use and we implement the free energy with RBM, reduced Boltzmann machines, very efficient machine learning approach again. And what we do is we build the baseline model, the green area there, and then we actually have some spurious KPIs, so we tell you whether they're anomalous or not. And what we get is we get a precision, 95%, I recall 99%. We get a performance which is about 24 seconds of prediction time. We get an overhead which is about 2% of the CPU time. So eventually what we have is we have a precise failure prediction, we have no fault localization, but we have a negligible overhead and online incremental training, almost all done. Precise prediction, no overhead, incremental training, which means if your system changes every 5 minutes, we can follow it. Oh, but we cannot tell you where. And so we moved on, and we moved on with the third part, the second part, which is fault localizer. Quick to stay in time, fault localizer, we use KPI ranking. You know, I'm sure you are familiar with page ranking, you know, the famous success of Google, who can actually tell you what you want to listen, to learn from your research. And instead of ranking pages, we rank KPIs. What we do is very simple. We generate a graph. This is called the KPI causality graph. It's a bit complicated technically, but basically you have different KPIs and different relation between KPIs. And then we actually, the correlation shows which KPIs are related to each other when one KPI changes the same time as the other. And so what we go is we actually get on this element the spurious or the anomalous KPIs. And from the anomalous KPIs, we can actually study the evolution of the KPIs and we can actually locate the failure. How do we locate the failure? Well, this is a big diagram with many experiments because we do many experiments. We've been working for years on that. You know, packet loss, memory leak, CPU hogs. We've been experimenting with different kind of failures, and we got very, very good precision, up to 100% on page ranking. Okay, which means basically we compare our failure predictor with the fault localizer, which is precise with no training and no overhead. And now the very last step, which is basically here. We can predict the failure, great. We can locate the fault, great. Now, don't expect the location be like that statement is wrong. It says that server may actually work badly, that application might work badly. So what you want to do, of course you want to pass all this information to your favorite developer and say, can you fix it, please? But you know, you remember probably, I think it was United, half a day of downtime because of a stupid fault in their ticketing system, in their boarding system. Okay, it took half a day to the whole staff of technicians in United to fix a problem where every minute was a flight not leaving. So we want to do something different, which is do something automatically, which is basically want to heal automatically. It doesn't mean correct the fault, it means work around the fault. How do we do that? Well, very simple. We generate workarounds. That's exactly what you do. You know, you go to the airport, you don't have your ticket, but you have your passport. You don't have your passport, but you have your name and your ID. So you try to find a different way to get the same result. What is the great thing that we are doing? We are trying to generate them automatically. How do you do that? Well, we work on this idea, which is the idea of using, I call them natural language processing. Oh, yet another thing that doesn't have anything to do with what you are doing, you know? What are you doing with natural language processing? That's a key idea. Think about applications. Think about every system you have. You know, you need to actually learn how to work with Uber. You need to learn how to actually walk in a smart city. What you do, you try with the system, and then you look at the blogs, you look at the reports, you look at fault repositories. There is a lot of information in terms of natural language, in terms of the diagrams, in terms of videos, in terms of tutorials. And it tells you, for example, that a thread is found is equivalent to search from danger. It's easy to understand if you're a human being. Now, with what we call word embedding and word move distance, and I'm ignorant, I just learned from my colleagues who's working, that's interdisciplinary, who are working on natural language processing, you can basically automatically relate the two things. So you can know that A is equivalent to B, or almost equivalent, or enough for that specific input. And we do that automatically to put in the things. So basically, we use natural language processing to automatically identify what we call workarounds. Okay? So, summing up, because it's time to actually give time for the next step, is what we do have is a failure prediction. What is the status of our research? Extensive experience with data analytics, machine learning, deep learning, excellent results on large-scale industrial systems. We have been experimenting with our previous, and we experiment with Acronis. We are experimenting with the disaster recovery system of Acronis about getting these things. We do have data from other partners, and we are getting data from Acronis. And we do it for packet loss, packet corruption, packet latency, CPU hogs, memory leaks, etc., for many different kinds of failures. Fault localizer, machine learning KPI, also here we did actually a very good experience industrially speaking, and the same classes of faults, of course, because you want to locate the faults you actually can predict. Healer, we have some experience on a small scale, and that's what we are doing now, and we will actually work more and more, and I'm hiring, by the way, 5 new junior members of the group to do more job on this one. And so basically what we have is we have an evolving and ongoing things. Now, conclusion, why I'm here. I'm here because we have a strong partnership with Acronis. We are actually working on a new project. It just started because we started as an institution 3 months ago. I started a bit before because I'm not new actually in the science environment. We are collaborating with the people who are working with backup and disaster recovery cloud. And what's the problem there? Say, look, how the hell you actually help people finding failures on a system that should actually prevent failures to happen? Am I actually discouraging you? No, the point is that there are failures that I call hidden backup failures, and this is my term, which basically means, you have this fantastic system that keeps you the backup for your system, and then it may happen that you have a failure, hopefully not, but it may happen. You don't want definitely to discover that when your system has crashed and the backup is not there anymore. It's done already manually. It's very expensive for Acronis. We will do it automatically, partially automatically. It's going to be much, much more efficient and much, much more precise. So that's what we actually are trying to do with the company in hopefully the near future, in the midterm future. Okay? So the plans are to go from what we have been doing now, which is classic cloud, static cloud, I call it, to highly dynamic cloud, and we are working on deep learning, on energy-based, on dynamic evolving systems. I showed that to you. We want to move from functional and performance issues, which is what we have been aiming at the moment because of the past partnership, to cybersecurity issues, and we'll do that with Acronis. And we are working on simple automatic workarounds. So we have been working on at unit level to pervasive automatic workarounds. And I guess the protocol does not allow you to ask questions right now, but I'll be around. This is my references, and I'll be in the space for the rest of the day. Thank you.